All right, so now things get to be pretty exciting. We're getting into enzyme function in this lecture series. This will be a three-chunk lecture, A, B, and C, and we'll really start scratching the surface of biochemical principles and start talking about the amazing things that enzymes do. Enzymes, of course, being protein machines. We'll introduce those concepts here in this first lecture, and these three lectures, these three chunks, make up the first half of Chapter 6. We spend quite a bit of time on these Chapter 6 concepts. In this chunk, we'll be talking about enzyme kinetics. Enzyme kinetics are the speed or rate of biochemical reactions that are catalyzed by enzymes. And we'll be tying those concepts in with thermodynamics, which is essentially the idea of making the universe happy. Making the universe happy with energy and with randomness, and we'll talk about that a little bit more when we get there as well. In the next chunk, we'll talk about determining the rate of catalyzed reactions, truly getting to enzyme kinetics, the true biochemical field of enzyme kinetics, and then we'll talk a little bit about enzyme substrate binding as well. So, before we talk about enzymes, let's talk about catalysis. Catalysis in general is the act of speeding up any chemical reaction, making that reaction occur more rapidly, and therefore making that reaction occur more quickly and more easily. So this is a bit of an old picture of my two little monsters, Charlotte and Maddie, Charlotte on the left and Maddie on the right. And this picture was taken when Maddie was 5.5 years old, Charlotte was 7.5. And back then, I mean, still even now, Maddie is as slow as can be. But back then, getting Maddie to put her shoes on was like pulling teeth. It would literally take 15 minutes for this little girl to put on shoes. And when you're in a rush to get out of the house, especially as a parent, nothing wants you to make you pull your eyeballs out more than this kid taking 15 minutes to put on shoes. This is a more recent picture, taken much more recently. Charlotte now on the right and Maddie on the left. I guess it's fair to say Maddie's a little bit quicker with her shoes, but still, for an 8-year-old, how long can it take to put on shoes? Anyway, when this happens, I would often and still become the catalyst, and I would be the catalyst by saying, "Come on, Maddie, let's go, we're running late, hurry up." And she would move at a faster rate, still slower than your average human being, but faster for her. So I'm speeding up what's happening. Without catalysis, without my urging, that reaction, that putting on of shoes, would occur much more slowly. By urging her to move faster, I get that same process to occur much more rapidly. And chemical catalysis is the same way. Without catalysis, the reaction occurs, but it occurs more slowly and with difficulty. With the catalysis present, that same reaction occurs much more rapidly and more easily. Now, here's the key concept, though, with catalysis, and we'll go back to the analogy. Either way, Maddie puts her shoes on. The reaction starts with her shoeless, and it ends with her shoes on. All I did was speed that process up, and the same is true for chemical catalysis. The end result doesn't change. The overall reaction itself does not change. Whatever you start with and whatever you end with is the same whether catalysis is in play or not. The only thing catalysis changes is the rate of that reaction, how quickly that reaction occurs, and catalysis, of course, is making that reaction occur more rapidly. So of all the things that proteins do in general, and remember we talked a little bit about fibrous proteins being structural in the last lecture series, and there are plenty of amazing things that proteins do. Catalysis by protein enzymes is by far the most fascinating and the most important. Without these protein catalysts, without enzymes, the chemistry required to make life possible would simply take too long, and therefore life would not be possible. Enzymes make life possible. Enzymes are, probably not surprisingly, globular proteins. They take on this roughly spherical shape. It's also important to note, and we've just hinted at this on the last slide, that not all proteins are enzymes. Very roughly, we could kind of diagram protein composition with this pie graph. And enzymes make up about 1/3 of all proteins that are out there in life. The other 2/3 are, of course, non-enzymatic proteins. It's even fair to say that not all globular proteins are enzymes. Here, enzymes do make up the majority. Most globular proteins are enzymes, but there's a fair number of globular proteins that are not enzymatic. And by not being enzymes, all we mean is that these non-globular these non-enzymatic globular proteins simply don't catalyze reactions. They do other jobs in the cells. They don't make reactions occur more rapidly. It's also important to note that you can have chemical catalysis of biochemical reactions independent of proteins in general. Specifically, there are unique RNA molecules that can fold up into three-dimensional shapes that achieve biochemical catalysis. They can speed up biochemical reactions. Because these molecules are RNA, we can't call them enzymes. Enzymes is a term for proteins only. So we call these molecules ribozymes to emphasize that they are ribonucleic acid, but also enzymatic in nature. So ribo for the RNA part and zyme for the enzyme part. These are catalytic RNAs. They're not proteins, they're RNA, but they definitely catalyze chemical reactions. We won't say anything more about ribozymes in this course because this is a protein biochemistry course, but do know that ribozymes are out there and they do amazing things themselves. I'll slip this in here because I think it's fascinating, but the enzymatic, air quotes, the enzymatic component of the ribosome is actually a ribozyme. The ribosome's catalysis of making the peptide bond is catalyzed by a catalytic RNA, not an enzyme. So enzymes, though, protein enzymes, are amazing catalysts. They do amazing things. This table is from your textbook, and it shows some of the enhancements of biochemical catalysis given by enzymes. Here on the left side, we have reactions in their non-enzymatic half-life. So this is how long it would take for the reaction to go halfway to completion when an enzyme was not present. And on the right, we have the catalyzed rate of the reaction, how quickly it takes for the reaction to occur when the enzyme is present. And here's the enzyme under consideration. So let's focus in on a few of these. We see that the enzyme carbonic anhydrase catalyzes a biochemical reaction. That reaction takes about 5 seconds to go to completion without the enzyme present. That's a rate of about 1/10 of a reaction every second. So if we look at this rate here, this is basically telling us that it would take about 10 seconds for this reaction to occur on its own, a single reaction to occur on its own in the absence of an enzyme. Not bad. 10 seconds is not a long time. So if it takes 10 seconds for a reaction to occur, not so bad. If we look at the catalyzed rate in the presence of the enzyme, we see that we get 1 million reactions per second. Think of that. 1 million reactions per second. Without the enzyme, 1 reaction every 10 seconds. With the enzyme, 1 million reactions per second. Unbelievable. If we look at another, we see here that it would take, well, I can't even do the math. It would take 28 and follow that with 15 zeros seconds for a single reaction to occur. That's a long, long time. 28 followed by 15 zeros worth of seconds for one of these reactions to occur. Add the enzyme, and you get 39 reactions every second. An incredible rate of enhancement. So again, we made the point earlier, but enzymes allow life to be possible because enzymes speed up biochemical reactions at rates that are suitable to make life possible. These reactions would simply take just too long in the absence of enzymes, but with enzymes present, they happen fast enough for life to be possible. Going back to Maddie's shoes, the actual reaction that's occurring is no different in the absence or presence of the enzyme. You go from products to reactants either way. The only thing the enzyme is doing is speeding that process up. Enzymes are the best catalysts out there. There are non-enzymatic biochemical catalysts like certain metals, and they do a decent job of speeding up chemical reactions, but not like enzymes. Nothing speeds up chemistry faster than an evolved protein enzyme. Enzymes also offer something that is important for life, which is specificity. The idea of specificity is that an enzyme will only work on a very specific set of reactants and speed that reaction up into products. In this way, we can't have one enzyme catalyzing or influencing multiple different reactions. Each reaction has and requires its own specific enzyme that can only catalyze that one reaction. And this is important for a cell when you're trying to regulate or control things. If you want one reaction to be sped up, you can make that enzyme, express that gene to make that protein so that reaction goes faster. And as the cell, you know that the only reaction that will now go faster is the reaction you've expressed the enzyme for. So it allows the cell to pick and choose which reactions occur slowly and which reactions occur more rapidly. All right, so we have a good idea now of what we mean by catalysis and what enzymes are doing with regards to catalyzing reactions. So let's tie that into these ideas of kinetics and thermodynamics. Kinetics and thermodynamics are very closely related concepts, but they are different and distinct as well. So we'll try to make their differences apparent here while also tying them together at the same time. And everything we say about kinetics and thermodynamics is going to be true of all biochemical reactions, whether they're catalyzed or uncatalyzed. We'll throw in the influence of enzymes as we get comfortable with these concepts as well. So let's talk about thermodynamics first. To understand thermodynamics, we really have to think anthropomorphically about the universe. And what I mean by that is I'm going to start ascribing emotions to the universe. This is a quick and easy way to get at the idea of what's being favored and unfavored by universal principles. But let's think about the universe as a sentient consciousness that has some feelings. So if we do that, and we go with that supposition, the universe likes, air quotes, it likes free energy. The universe likes heat. The reason why the universe likes heat is because the universe favors entropy. This is probably a concept that you've encountered before in your chemistry classes, and probably in physics as well if you've taken physics thus far in your curriculum. The reason why the universe likes free energy, the reason why the universe likes heat, is because when free energy is released, when heat is released into the universe, it makes things move more rapidly. Think of boiling water. The hottest water you can achieve is boiling water, water at 100 degrees centigrade. And that water is much more dynamic and moving much faster than still water is at a cooler temperature. So that's true of all things. When heat is released into the universe, when heat is released into the environment, molecules move more rapidly. And more rapidly moving molecules are more random molecules. They're more chaotic. Entropy goes up, and the universe likes that. So the universe likes when free energy is released because the universe likes when molecules move more randomly. So, the universe likes, and therefore the universe allows any reactions to occur that release free energy. That means heat will be given off by those reactions. These are exothermic reactions, and that heat will speed up molecules, making things more random. On the flip side, reactions that absorb free energy, reactions that take free energy out of the universe, therefore cooling that area down, are stealing free energy from the universe, making molecules move a little bit less, making things move a little bit more slowly. Think of ice in this example, the most ordered, least chaotic form of water. Why? Because it is the coldest that water can get, 0 degrees centigrade. And such reactions make the universe sad. The universe hates nothing more than order. The universe prefers randomness and entropy. So reactions that cool the universe down, endothermic reactions that take up free energy, make the universe sad, and therefore the universe will not allow those reactions to occur. If you understand those general principles, then you've understood thermodynamics as much as you need to for biochemistry. Reactions that release free energy and give off heat are allowed by the universe because they speed up molecular motion and increase entropy. Reactions that absorb heat from the universe, take up heat, and cool the universe down are not allowed by the universe because they slow molecules down, decreasing entropy. So, what that means for us is if we want to determine whether or not a reaction will occur, if we want to determine whether or not the universe will allow a given reaction to occur, we need to first determine whether or not that reaction releases free energy. If the reaction releases energy, the universe will let it happen. If the reaction absorbs free energy, the universe will not. To do that, we need to look at the free energy that is contained within the molecules of the reactants, that's what we start with, and compare it to the free energy contained in the molecules of the products. That's what comes out at the other end of the reaction when it's completed. We call this the change in free energy, and we represent it as delta G. The triangle here is referred to as delta, and G, of course it makes perfect sense that we use G to refer to energy, which starts with E, or heat, which starts with H, but we use G. Okay, so what we're really saying here is that delta G, the change in free energy, is mathematically equal to however much energy you had in the products minus however much energy was present in the reactants. That's your delta G. If the change in free energy of the products is less than the change of free energy of the reactants, in other words, let's say this value is 3 and this value is 5, that means the energy in the products is less than the energy of reactants. Well, 3 minus 5 is negative 2. And a negative change in free energy means that energy was released. If you have 3 units of free energy in the products when you're done, and you started with 5 units of free energy in the reactants when you started, then that means the difference, those 2 units of free energy, were released by the reaction to the universe as heat. And that heat made molecules move faster, it increased entropy, and the universe was very, very happy. So let's look at this schematically and see if we can figure out which one of the reactions the universe likes. These are referred to as free energy diagrams. And we see time of the reaction on the x-axis and the amount of free energy on the y. You can think of this as numerical. So this is 0 units of free energy, maybe 2 units, 4 units, 6 units, 8 units, and up you go. So in this reaction, there's a certain amount of free energy in the reactants. The reaction occurs. Don't worry about this blip in the center quite yet. We'll get there in later lectures. The reaction occurs, and then you end up with products. Here, the value of the free energy of the products is lower than the value of the free energy of the reactants. In this diagram, we start with reactants, and in the case, the energy in the reactants is the same as the diagram on the left. The reaction occurs, and we end with the products, and in this case, the free energy in the products is greater than the free energy of the reactants. Think about what we've already said. Look at these 2 free energy diagrams and see if you can figure out which one of these reactions will occur. I'm going to answer that question in just a second. If you'd like some time to think about it, please pause the lecture. It's the reaction on the left that's going to be favored by the universe. If we do give some numbers here, let's say that this is 8 units of free energy in the reactants. Reaction occurs, and we're down to 4 energy units in the products. That means that 4 energy units was lost when we went from reactants to products. We started with 8, and we ended with 4. The remaining 4 units of energy were released by this reaction as heat, and that made the universe happy because it increased entropy. Here, we start with 8 units of free energy in the reactants, and we end with the products having even more free energy, 12, let's say. That means 4 units of free energy had to be absorbed from the universe in order to allow this reaction to occur. That cooled the universe down, made molecules move less rapidly, and decreased entropy, and the universe hates that. So the reaction on the left is favored by the universe, and the reaction on the right is not. Any reaction like the one on the left that has a negative delta G, when you go from 8 to 4, your delta G is a negative 4. These are called spontaneous reactions. The universe wants these reactions to occur because they release heat. They release free energy in the form of heat, and that increases entropy. If we consider the reaction of glucose and oxygen to make carbon dioxide and water, this is the very reaction that we will end the course with. Believe it or not, we're going to spend something like 7 lectures on this reaction, because this is the reaction that keeps us alive. This is the reaction that fuels our entire lives. We consume glucose, we breathe in oxygen, we exhale carbon dioxide and water, and the balance of that energy we use to make ATP, which keeps us running. This reaction is enormously favorable and spontaneous, and it releases tons of free energy. In fact, the delta G of this reaction is negative 2,880 kilojoules per mole. Trust me when I tell you that's a lot of energy. So this is how we get our energy to survive. What I'd like you to do, if you can, is go to your cupboard, if you have one handy, and I'll do the same. Get yourself some glucose. Sucrose will do. Sucrose is table sugar. It's about the same reaction. And I want you to very, very carefully now carry that table sugar to wherever you are. Be very, very careful. I'm doing the same. And I want you to very, very carefully pour that sugar, a little bit of it, onto the desk or tabletop in front of you. Be careful. I'm doing the same. Remember, there is plenty of oxygen in the air that we are breathing. That's what's keeping us alive. And as soon as that sugar touches oxygen, it's going to release negative 2,880 kilojoules per mole. Be careful. Here I go. I'm about to do it myself. I'm going to spill some of that sugar right onto my desk here. And nothing happened. That's crazy. If you look at the delta G here, this should have blown up right in my face and singed my eyebrows. Same for you. And yet nothing happened. Why? Well, let's take a closer look at this free energy diagram. When we consider delta G, all we're looking at is the free energy of the reactants and the free energy of the products. In fact, we are not considering the path between the two at all. When I tell you that the reaction of glucose and oxygen gives carbon dioxide and water and tons of energy, I'm saying that if you start with glucose and oxygen, you'll end with carbon dioxide and water and tons of energy released. But we're not really considering how we got from point A to point B. If we look at the path of the reaction, we will see that to go from reactants to products, there's a very high energy hill to climb. Remember, this is a free energy diagram. So what this is really saying, if we read this free energy diagram as a story, is that to go from reactants to products, we start with a certain amount of free energy in the reactants, and we have to add lots of energy. Lots of energy. All this energy we have to add to this reaction. That energy comes from the universe. All that added energy cools the universe down and makes things very cold and non-chaotic. The universe is not happy. Once we get to the peak of this energy requirement, then everything collapses. All the energy we put in comes out. In addition, even more energy emerges. That would be the negative 2,880 kilojoules per mole. And finally, we end with products. What this diagram is telling us is that while the universe might want this reaction to occur because there's a huge energy payoff at the end, to get that payoff, the universe must invest lots of energy in the first place. You can liken this to me telling you, hey, if you give me money, I can make you a profit. I can get you money for investing with me. And you say, okay, you're going to make me money for nothing? I'll invest with you. So I say, all I need is the money you start with, and I'll make you a huge profit. All I need is the energy you start with, and I'll release tons of energy into the universe for you. Say, okay, sign me up. I say, okay, so here's how it's going to work. We're going to start off with where you are now, and you're going to give me $10,000. And once you give me $10,000, I will be able to make you another $30,000 profit after that. That's the payoff. And if you're anything like me financially, you're going to say, well, I'm out. I don't got 10 grand, so sounds great, and I trust you, but I'm out. Large investments, even for huge payoffs, are not favorable for us financially, and they're not favorable for the universe thermodynamically. The universe is not into investing energy to make payoffs. So the reason why this glucose didn't blow up in our faces is because even though there's tons of energy profit to be made by that reaction, the universe at room temperature was not willing to invest the energy needed to get that reaction to progress towards completion. So, key point of all this is that when we say reactions are spontaneous, just as the reaction of glucose and oxygen is, that is not synonymous with instantaneous. Spontaneous reactions do not occur instantaneously. because of these energy requirements to get there. As an analogy, we might say that the hotel in Yaletown, here on this map, is very close to the hotel in downtown. It looks here like it's something on the order of 8 city blocks. Looks great. Pretty quick. That's not far at all. I could walk it. But if I put Mount Everest between the two, they ain't so close together anymore, are they? Not really a walkable distance, is it? That mountain is the energy mountain between our reactants and products energetically. It might be a short energetic distance between the two, but not if there's this huge energetic barrier between the two. It may be thermodynamically favorable with a negative delta G to get from reactants to products, but not so if this mountain of free energy requirement is between them. This mountain of free energy requirement, the energy it takes to get from here to here, the point of collapsing, is called the energy of activation, and every biochemical reaction has one. This is abbreviated delta G double dagger. This symbol is referred to as a double dagger right here. And so if we look at another free energy diagram, we see that this reaction also has a negative delta G. The amount of energy in our reactants is higher than the amount of energy in our products. This is a negative delta G change in free energy. This is a favorable reaction. It is spontaneous. But to get that energy out, we have to climb and invest this energy hill. This energy hill, from the energy of the reactants to the top of the peak of this free energy diagram, is delta G double dagger, the free energy of activation. Enzymes are path independent. Enzymes never affect delta G. Instead, what enzymes do is they lower delta G double dagger. Enzymes work by lowering the energy of activation, making this hill lower. In other words, in the presence of an enzyme, the universe needs to invest far less of its own energy into the reaction to get it to go to completion. This reaction free energy diagram shows that. The dotted line shows the free energy diagram in the absence of an enzyme. The blue line shows the same exact reaction in the presence of an enzyme. You'll notice that the free energy in the reactants and the free energy in the products is unchanged, whether an enzyme is present or not. What the enzyme did was lower this energy hill and make it go from a $10,000 requirement for investment to a $100 requirement. If I came to you and said I could make you $100,000 profit and all you needed to do was invest $100 with me, you might take that chance. And so too would the universe. Smaller energy investments are more favorable, and enzymes allow those energy investments to be smaller by lowering the energy of activation. How enzymes do that is something we'll cover in a later lecture chunk, but that's what enzymes do to catalyze biochemical reactions. All enzymes do, and all catalysis does, to improve the chances of a chemical reaction occurring and make those reactions occur more rapidly, is lowering delta G double dagger. And we go from an energy hill that is insurmountable because that hill is too high to, in the presence of an enzyme, lowering that hill and making it surmountable so that the reaction can go to completion. So enzymes make reactions more easy, and enzymes make reactions occur more rapidly by affecting these thermodynamic principles of energy requirements. That's where we tie into kinetics. If we're talking about reactions occurring more easily, energetically, an easier reaction occurs more rapidly. It's a faster reaction. And kinetics is the notion of the speed of a reaction. If we go back to the hotel analogy, if I get that mountain out of the way, you will get from downtown to Yaletown faster because you get there easier. If you don't have to climb the mountain because the enzyme has removed it, it's an easier trip and a faster trip as well. Enzymes do not change the energy of the reactions, they only change the energy of activation. They lower delta G double dagger. So let's just test your general comprehension here. Take a look at this diagram. We've got 3 differences in energy represented. We've got A being the distance in energy from here to here. We've got B representing the difference in energy from here to here. And we've got C representing the difference of energy from here to here. And I'm asking you which one of these letters, which one of these energetic differences represents the energy of activation. Go ahead and pause it if you need some time to think about it. I'll answer it in about a second or two. The energy of activation, also known as delta G double dagger, is represented here by A, the amount of energy to get from the reactants to the peak of the graph. We don't name C in this course. B is representing delta G itself, the change in free energy. That's the difference in energy between the products and the reactants. So to summarize what we've talked about in this lecture chunk, we started off defining catalysis as the act of speeding up a chemical reaction and making it more easy to occur. We made sure to understand that the universe encourages reactions that have negative delta Gs. These are reactions that release free energy. The reason for that is that the universe likes heat being released because it makes things more chaotic. If the free energy of the products is lower than the free energy of the reactants, we will have a reaction with a negative delta G. That means free energy is released, and those reactions are favored by the universe. We call that thermodynamically favored. We can also call that a spontaneous reaction, a reaction that the universe will allow, but spontaneous reactions are not necessarily fast or instantaneous because of that energy hill. The energy of activation is the amount of energy investment needed in order to get reactants to proceed to products, and if that energy of activation requirement is high, that reaction is unlikely to occur at room temperature. What enzymes do to catalyze biochemical reactions is they lower the energy of activation, making the energy investment requirement of the universe that much lower. This encourages reactions to occur more easily and to occur more rapidly. Nothing else about the chemical reaction has changed. Products and reactants remain the same, as does delta G. So we'll talk a little bit more about how enzymes work and how enzymes get you from reactants to products in these upcoming lecture chunks. As always, thank you for watching.